Right now, inside the device you're watching this on, a dozen different components are working together millions of times per second. Each one has a single job, and if any of them failed, the whole thing would go dark. In the next 12 minutes, we'll open up a computer and explain every major part, what it does, how it works, and why it matters. Let's take it apart. Every computer, from a gaming tower to a phone, follows the same basic recipe. A brain to think, memory to hold what it's thinking about, storage to remember things long term, a power source to feed it all, and a way to move data between them at incredible speed. The differences are just size and power. Let's start with the piece everything else plugs into. This is the motherboard, the foundation of the entire machine. Think of it as a city's road network. It doesn't do the thinking itself, but every other component plugs directly into it, and it carries power and data between them through thousands of microscopic copper traces etched into the board. The big socket in the center holds the processor. The slots hold memory and the graphics card. Everything connects here, which is why the motherboard decides what parts your computer can even use. At the heart of it all sits the CPU, the central processing unit, the brain. Its only job is to do simple math, but it does it billions of times every second. It pulls in instructions, calculates a result, and sends it back out over and over, faster than you can imagine. Modern CPUs pack several cores, which are basically multiple brains working in parallel, so the computer can juggle many tasks at once. When people talk about gigahertz, they mean how many of these cycles the chip runs per second. But the brain needs a workspace, and that's RAM, your computer's short-term memory. When you open an app or a game, it gets loaded from storage into RAM, because RAM is hundreds of times faster to reach than a hard drive. The CPU keeps everything it's actively using right here. The catch? RAM is volatile. The instant the power cuts out, everything in it vanishes. That's why a crash loses unsaved work, and why more RAM lets you run more things at once. Now the muscle, the GPU, or graphics card. If the CPU is a brilliant manager doing a few complex tasks at a time, the GPU is an army of thousands of simpler workers all doing the same task at once. That makes it perfect for drawing millions of pixels on your screen. And it's exactly why GPUs also power AI and video editing. It's almost a whole computer of its own, with its own processor and its own super-fast memory, all dedicated to one thing: massive parallel number crunching. Everything you save needs a permanent home, and for decades, that was the hard disk drive. Inside is a stack of spinning metal platters coated in magnetic material, and a tiny arm that floats nanometers above them, reading and writing data as bits of magnetism. It's basically a record player operating at thousands of RPM. Hard drives are cheap and hold enormous amounts of data, but because they rely on physically moving parts, they're slow and fragile compared to what came next. That successor is the solid-state drive. An SSD has no moving parts at all. It stores data in flash memory chips as trapped electrical charges. With nothing to spin up or move, it's dramatically faster, silent, and far tougher. This is why a modern computer boots in seconds instead of minutes. The fastest ones plug straight into the motherboard and move data many times faster than any hard drive ever could. None of this runs without clean power, and that's the power supply unit's job. The electricity from your wall socket is high voltage alternating current, far too crude for delicate chips. The power supply converts it into the steady, low voltage direct current that every component needs, splitting it into precise streams for the motherboard, the processor, and the graphics card. Get this part wrong, and an unstable supply can quietly damage everything else. All this electricity becomes heat, a lot of it, and heat is the enemy of every chip. That's why cooling exists. The simplest version is a metal heatsink that pulls heat off the processor, with a fan blowing it away. Push harder, and you move to liquid cooling, where fluid circulates through the hot parts, carries the heat to a radiator, and dumps it out the back. Without cooling, a modern CPU would overheat and shut down in seconds. All of this lives inside the case, and it's more than just a box. It holds everything in place, protects the delicate electronics, and most importantly, it directs airflow. Cool air is pulled in the front, swept across the hot components, and pushed out the back and top. A well-designed case keeps a powerful computer running cool and quiet. A bad one turns it into an oven. So how does all this talk to each other? Through the chipset and the buses, the computer's traffic control, and highways. The chipset manages the flow of data between the processor, memory, and everything else, deciding what gets sent where. The buses are the lanes that data travels on, and the wider and faster they are, the more information moves at once. This invisible network is what turns a pile of parts into a single working machine. But when you first hit the power button, the computer doesn't even know what it is yet. That's where the BIOS comes in, a tiny program stored on a chip on the motherboard. It's the very first thing that runs, waking up each component, checking they all work, and then handing control over to load your operating system. It's the spark that brings the whole machine to life. Of course, a computer is useless if you can't connect anything to it. That's what ports are for, the inputs and outputs along the edges. USB carries data and power to almost anything. HDMI and DisplayPort send video to your monitor. Ethernet plugs in the internet. Each port is a doorway with its own shape and speed, letting the machine talk to the outside world. And to reach the internet, the computer needs a network connection. A network card translates the computer's data into signals that travel down an Ethernet cable, or, with Wi-Fi, into radio waves broadcast through the air to your router. Either way, it's packaging your data into tiny packets, firing them across the world, and reassembling the replies, all in milliseconds. So, let's put it in motion. You click an app, the CPU asks for it, and it's pulled from the SSD into RAM. The CPU processes the instructions, handing the visual work to the GPU, which paints it onto your screen. The power supply feeds every step. Cooling carries the heat away, and the chipset shuttles data between all of them, billions of times a second, smoother than you'll ever notice. That's not a pile of parts. That's a computer. Here's the practical takeaway. For everyday speed, more RAM and a fast SSD matter most. For gaming and video, the GPU is king. For heavy multitasking and raw work, it's the CPU. And whatever you build, never cheap out on the power supply or the cooling. They quietly protect everything else. Match the parts to what you actually do, and you'll never overpay for power you'll never use. So there it is, every major part of a computer. The motherboard connects everything. The CPU thinks, RAM remembers for now, storage remembers for good. The GPU draws your world, the power supply feeds it, cooling keeps it alive, and the chipset ties it all together. Individually, they're just silicon and metal. Together, they're the most powerful tool humanity has ever built. From a single transistor to a machine that fits the world in your pocket, that's the computer, part by part. If this made it all click, there's a whole series of these breakdowns waiting for you. Subscribe, and we'll see you in the next one.